Hi everyone, this is a demo of Irontools, a suite of Flink extensions that make Flink more efficient and unlock new use cases. This demo is about iron functions. This extension allows you to execute your business logic in different languages like TypeScript, Rust, Golang, so languages that are not typically provided by Flink, not supported by Flink. And this is possible thanks to a fast and secure WebAssembly runtime that we use in Irontools. And this demo focuses on the table in SQL API, and we're going to be building a UDF jar and deploying it onto Confluent Cloud as an example. Please go and check the DataStream API video as well if you're interested. And so, to start, let's see what kind of data we have. So, in Confluent, we have a couple of topics, test, start geo, and test end geo. So these topics, they have some kind of travel information. So this is all fake data, but we have a trip ID, some kind of payload, just numeric field, city, and its coordinates. And the way the system works is, imagine for each trip, we emit a record at the start of the trip, and so it's emitted to this topic, start geo, and then at the end of the trip, we emit another record to the end geo topic. Hopefully this makes sense. And so to start, let's see if we can actually join the data using this trip ID. Let's see if this is gonna show anything, right? So I'm running this query, which is taking start city and start coordinates from one table or one topic, joins it on trip ID, and gets the end city and end coordinates from the other topic, right? So this is what we have. Don't need to look for any pattern. This is all fully random fake data. But let's say we want to compute a new column here, distance, right? So we want to see how far is, what is the distance between start and end. And you can't really do this out of the box, so we're going to be using Irontools TypeScript function to do that. And we're not going to be building a lot of this logic from scratch. I want to show you how easy you can import an existing library. So I found this geoleap library that has exactly the method that we need here, get distance. This method takes your start coordinates, your end coordinates as inputs and provides you with the distance, right? So let's create a new project. We're going to be using this ironfung CLI, and the generate command accepts your project name, language, and the output path. So very easy. Created this project. It's a typical npm TypeScript project. Let's open it in an ID. So here, as you can see, we have a README, we have standard package JSON, and our sort of scaffolded main function. According to README, we need to install this Xtism.js compiler, and Xtism is a great WebAssembly framework that Irontools use to interact with WebAssembly. So I already have that installed, and in the future, of course, you won't need to really install it as a separate step. Iron functions will come with that support. We do need to run the npm install to get all the dependencies installed, and if you look in the package.json file, you'll see that we only have the Iron Functions SDK as the dependency right now, and some type dependencies to make it easier to build TypeScript. And we have one built script that compiles our JavaScript or TypeScript into WebAssembly. So let's see, npm install is done. So now if you go to our scaffolded function, you should see that it's a simple process function. It has to be exported, and we get input from Flink using this flink.read. It can be any object. We can also use a class to represent the input of that object. And we simply write the data using flink.io.write. Let's try to build this file first, so using npm run build, and actually trying to run a simple test first, right? So to do that, we're going to be using this xtism CLI. Again, comes with the xtism framework, and we simply call the process function, and we pass some input, which has to be valid JSON, because this is the format that we're using to interact between WebAssembly and Flink right now. And we call it, we get exactly the same data back, right? So our scaffold, by default, simply takes the input, writes it back as the output. So now let's try to implement these UDF, and remember, we want to get the distance, and let's say for fun we want to add some prefix to the column, so it doesn't just print the value, but we also can add some random prefix. And so we need to install that geoleap dependency first, right? So simply npm install geoleap, there's our save. Now it's one of the dependencies, yep. And to implement the logic, let's start with defining our input and output class. Now, this is not strictly required for Irontools. You can use, you can deal with arbitrarily JSON. As you can see, any is valid. And this is something you can get away with for data stream API. However, for the SQL table API, because we're going to be generating a UDF jar, we need to define those inputs and outputs in a static way. So it's fully defined structure. So let's see. For the coordinates, we're going to be using a number type, array of numbers, right? Because this is what we have right now in our Confluent topic, right? So it's a simple array with 2 elements. And despite the name, TypeScript does not have many types. So in order to represent a float or double, we still have to use a number type. So chords x and y, and then our prefix, which is going to be a simple string. Okay, and for the output, we also define a class for the output. As I said, it's not necessarily required for the data stream API, but here we need it, and it's going to be a simple string. And we can make it a bit nicer by defining a constructor and just assigning the result to that constructor. Okay, so far so good. And now, because we have this input, we can use that here. And let's say, let's define our start coordinates. Gonna save some time by just copying what I have here, and the end coordinates similarly, right? So we need to format the data a certain way for the geoleap library, which we're actually gonna be importing here now. So we have these coordinates. Now, in order to calculate the distance, we simply gonna call geodistance and pass our get distance, and pass our start and end coordinates. All right, and then in order to create a result, we will use the prefix, right? So we have a prefix just for fun, right? We'll add the distance. Distance is in meters by default, so let's divide it, and let's append kilometers over here. And output as a result. Oops, typo. Okay, so far so good. So let's make sure this compiles first of all, and we can actually call our xtism CLI, but we have to provide the right payload now as an input. And so I save this payload, which shows you coordinates from London to Vancouver. And the distance is this value, which is correct. I double checked. So this is a distance from London to Vancouver, and these are the coordinates. So everything works. Now, unfortunately, because we are dealing with types that are not primitive, right? So we have an array of doubles or array of floats. We can't really understand that by just looking at this type, right? Because again, TypeScript only has number type, and you can't really distinguish between like big ints, floats. So in order to provide exactly what Flink understands, we can use a decorator. So Irontools, Iron Functions SDK comes with this Flink type decorator, and you can tell it exactly the type that you expect. So in our case, we expect an array of doubles, and same here, right? So in the TypeScript world, this can still be just an array of numbers, but for the Flink interface, we know it's an array, it's an array of doubles. And one more thing, because we're going to be using this UDF package command, we just need to let Irontools, Iron Functions know that this type is a Flink input. So we have a special interface. This interface does not require it to implement anything. It's just an indicator for the CLI to let you know that this is input or this is output type. That's it. So this is all we need. Now let's compile it again. Can double check that still works. Perfect. So now we will package it in a UDF file. So let's see. Package UDF. So this package UDF command accepts a source path. You tell it the package name and the class name of the UDF you want, the output path if you want to, and then you need to include a license file, because this UDF is going to be completely standalone. We're going to be deploying it on Confluent Cloud, and we're also going to make it an Uber jar in an environment where you control everything, right? Maybe it's a Flink that you deploy yourself. You can install license information. You can install Irontools, Iron Functions dependency in your Flink environment. But by using these two flags, we can make this UDF completely standalone, so it can be dropped into any system. Okay, so in order to compile, we will be using this package and class name -l -u for including license and including making the Uber jar, right? So that was fast, right? So it detected the input types, arrays of doubles, and our result type. And so now we can see that we have this geodistance jar in the project. This jar contains our WebAssembly logic, it contains all the dependencies, and we're going to be using it now here in Confluent Cloud. So first of all, we're going to register this as an artifact, and we're going to be using the Confluent CLI to do that. You simply need to provide the jar information, environment, region, and you get the ID and the version back. So these are needed to create a function using a jar file. So now let's register this function, and I have this new ID and new version that I to provide. Okay, let's run it. So we should get a geodistance function as a result. And while this is still working, let me show you the updated SQL statement that we're going to be using. Right, so this is exactly the same. Start coordinates, start CD. Oh, you see the function created, perfect. So I need to try to paste it again. Yeah, so start and the coordinates, and also the geodistance using this prefix. Yep, and still the same join. So this is our statement. Let's run it. So we should have this exact output plus an additional column with the distance, which is going to be nicely formatted. Let's see. Of course, this is an example with Confluent Cloud. You can use it with any Flink installation. As I said before, if you control your Flink installation, you can install Iron functions in your runtime, and then you don't need to build an Uberjar and include license information. If using Confluent Cloud or AWS Managed Flink or Delta Stream, Decodable, any of those tools that allow you to bring your functions, you can build an Uberjar with your license information and deploy it like this. So I think this is now going to output some data soon, finally. And just a reminder, this is a normal TypeScript project. It allows you to use any code you want, any TypeScript, functionality, classes, interfaces. You can structure the project anytime, any way you want. You can bring any dependencies, as long as those are not Node APIs and Node modules. This is the only restriction. And no like system calls or file system calls, because this function is running in a WebAssembly runtime, which is secure and sort of isolated. But as you can see, you can do a lot of things here anyway by just reading inputs, transforming, writing outputs, and you can use any kind of dependencies. Oh, finally, okay, it's done. It took a while, maybe first time to sort of register this function, but yeah, you can see now we get this distance information calculated for all those trips, which I think is pretty cool. And we didn't need to write a single line of Java or Python for that matter, right? And we created a custom EDF that does something quite useful and interesting, and we only had to deal with SQL and TypeScript, which is the goal of Iron functions. Thanks so much for watching. Contact us if you're interested, and see you soon.